Okay, so I already thanked Anamika, but I will thank her again. So the first talk will be about silicon photonics, a brief introduction. But before going into the topic, I would like to introduce myself, okay? So just so that you know who I am. And then, so the problem is that this is not going to be a brief, but it's going to be an introduction. So probably will be much longer than what was supposed, but I know that Indians are very strong people, and therefore, so I'm not scared to talk to you and to keep you here more than what is foreseen. Okay, now I can use, okay. So, University of Trento. So, University of Trento is in Italy. And Italy is in Europe. Should work. Yes. Okay, so University of Trento is in Italy. Italy is in Europe. So, this is Europe. This is Italy. University of Trento is in the very north part of Italy. And there you have a river, and then you have a city. It's quite an historical city. It's a small one. So in Trento, so you have something like 100,000 people living there. But what is characteristic of this place are the mountains. And in this period of the year, so the mountains means snow. So in Trentino now we have a lot of snow. This one is me. This one is me. This last Sunday, so I was there. I was skiing. So this is what ski means. And so you go there. You have a lot of snow. I was there in the wild, and then you ski and you go down, and you need to be scared because of avalanches. So it's not easy to go there. But anyway, so apart from skiing, what I'm doing, so I'm working at the university, so we do a lot of activity there. So this is the website of my university. Typically, in Italy, we do speak Italian, and therefore the website is in Italian. And this is people in my lab that were publishing a paper on nature communication. And therefore, so they put on the first page of the university. So the university is, Italian-wise, is a middle-sized university. We have more or less 50,000 students. And so the university is quite a generalist university, meaning that we cover all the different topics. So we have 11 departments, and we no longer have schools, we no longer have faculty, but we only have departments. Among those 11 departments, clearly, we have departments in engineering. But I, myself, I was the head of the department in physics a few years ago. And so I am a physicist. And then what else? So this is the castle, okay? So the castle is very characteristic. It's a medieval castle in Trento. And as you see, we are something like 700, so those are old numbers. But we have something like 700 students, 700 professors, 60,000 students, among which more or less we have 1,000 of foreign students. And so we do a lot of research there. So this is a research-intensive university. And most of the research are financed by the European Commission. So in Europe, so there are countries, but there is also the European Union. And the European Union is supporting a lot collaborative research between universities belonging to different countries. And so they are financing research, and my university is getting a lot of those funds. So then there are a ranking system like you have here in India, and the University of Trento is typically ranked in the top position. So either we are the first or the second or the third or the second or the first and so on. So we are always there. And so then about me, so I'm Lorenzo Pavesi, as you know. So I'm fellow of a few society. And if you Google my name, so this is me. And so you go to Google Scholar. So I did that last days. And you see the papers that we are working on. And what you can notice here is that so we do work on different topics, for example, on artificial intelligence. And despite I am a physicist, so I'm interested to understand what is happening. So we are also doing research that is industrial oriented. And here, for example, there is a patent that we got that is about on a novel kind of biosensor. I will talk you a little bit about that. And then those are the numbers, so, okay. And so there is this top Italian scientist I noticed just while I was Googling my name. And according to this ranking, I am 34, ranked 34 in Italy. You should consider that physics in Italy is essentially high energy physics, particle physics, so we have a lot of Nobel Prizes winner in that topics, or complex system physics and so on. And so I'm not bad. So this is my LinkedIn page, where typically I put my what we are dealing with. And what you see here in my LinkedIn page, that as a background image, I have one of the photonics integrated circuit that we are developing. So you can go there and you can ask to join my network. Okay, so this is about where I am. So how I make to reach there. So what are the different arguments that I have looked at during my career? So I started in 1985. My PhD in Switzerland, and at that time I was working on 3-5 semiconductors, and then at that time, so they were saying that 3-5 semiconductors are the semiconductor, at least were the semiconductor of the future because of the laser. But then I moved to Italy in 1990. I moved to Italy. I moved to Trento, and I started to work on silicon. And I will tell you why. But that time I was working on porous silicon. Then I did some work on silicon amplifier. Then I moved to integrated silicon photonics. And during early 2000, I started working on micro-ring resonator. I will tell you what those structures are. And then I moved to nonlinear optics because you have so beautiful phenomena that appears in nonlinear optics. And then I moved and I start working on try to implement a full optical network on an integrated chip. I will tell you something about that. And then during that time, since we are able to integrate functionalities on silicon chips, so we were also interested to develop biosensor. And a few startup companies raised about this biosensor. And then in 2020, I started working on integrated quantum photonics because of the start of the second quantum revolution. I will tell you about the second quantum revolution in a while. But at the same time, I started also working on neuromorphic photonics, meaning a photonics that get inspiration on how our brain is working. I will address those two topics during my courses. Any question? So what is important is that you interact. So whenever I say something that you do not understand, you raise your hand and you say, hey, tell me more about that, okay?
What is the medium of instruction?
Sorry?
What is the medium of instruction at your university? It is English or Italian?
Oh, that's a very good question. So the Italian system is organized in two levels. So you have the bachelor, 3 years, and then the master, 2 years. And then eventually the PhD if you are interested. And so at my university, we have that the bachelor is in Italian, but the master is in English. And so the master degrees, almost all the master degrees are in English.
So come for bachelor, they will have to learn in Italy.
Yeah, for the bachelor, yes. For the bachelor, yes, but for the master, English. And we have many Erasmus Mundus program, and there is one that is starting, I guess, next year on AI, and different platform for AI. So if you want, so the slides will be available. I will give the slide to Anamika, and so you will have all the slides, because I also give references. But a few years ago, when I got 60s, I decided to write a paper about what I did in the last 30 years in silicon photonics. And so if you are interested, so you can go. This is open access. This is the link. And here I make a little bit of review of my personal view of the field. And then I also edit a few books. So one of the first book on silicon photonics, then a couple of books on silicon nanocrystal, handbook of silicon photonics, and then the application of silicon photonics for light emission. And then those books you can find on, or you ask me, okay? You can find and you can buy. There is also the electronic version, or you ask me. So, silicon photonics. What do we mean by silicon photonics? But clearly, we mean integrated photonics. Integrated photonics means that we take a lot of different photonics components and we squeeze everything down to a very small circuit. And these are the kind of circuit that we are making. So this is 1 centimeter, this is 1 eurocent. And we do that in silicon. And so what we do is that we merge into the same silicon photonics chip both microelectronics as well as light. Okay, so this is what, in a nutshell, silicon photonics is. Okay, and the reason why we do that is because by doing that, so we have a lot of large functionalities that can be really integrated. So it's going to be easy. And so what we do in Trento, in my lab, is that we do the design and the testing. So with the design, we design the actual circuit, and we do test the actual circuit. So in my lab, we do not have any fabrication facility. And the reason is because nearby the university there is a research center that is called Bruno Kessler Foundation, which is just across the road. And in this Bruno Kessler Foundation, yes? So this is a very good question. And I think that I have a slide to answer you. So this is what we do by using silicon photonics. It's classical. So essentially, we do describe everything by using Maxwell equation. Okay, so this is what we are doing when I broadly speak about silicon photonics. On the other hand, when I do speak about quantum photonics, which I implement into the silicon platform, I say that what I'm using now is no longer the Maxwell equation, but I'm using the Schrödinger equation. Okay, so for me, the two fields are different. Apart from something that is nowadays appearing, where we try to merge the two, that is quantum machine learning. But I will talk about that later on. I cannot spoil my full week of lecture right now. But I hope that you get the point, okay? So today and tomorrow is going to be Maxwell equation, okay? Go back. And so I was saying that we, in this Bruno Kessler Foundation, so there is a facility that you can actually build the photonic integrated circuit, as well as you can package, so you can merge photonics and electronics. And this facility is led by some of my ex-postdoc or PhD students. Yes? Sorry? So they do that for money. I mean, so it's a business. Yes.
They do have that permission.
Yes.
Okay.
Yes.
Thank you.
So the way we do is that we are a fab agnostic in our design, because the fact that is you have so many facilities around the world where you can send your design and get the chip fabricated. Okay, so we are following more or less the same scheme as NVIDIA. You know NVIDIA, you know? Okay, yeah, boom. Exponential grow in the... So NVIDIA has exactly this model, and this model, fabless model, so without the fab, is the model that most of the big semiconductor giants are following. Apple, for example, NVIDIA. So there are two communities. So one vertical community like Intel. So Intel is doing from the design to the fabrication, to the package, to the test, to the selling of the components. So this is a vertical. On the other side, you have those companies that have decided not to do the fabrication in their own premise, but to use fabrication outside, like NVIDIA, for example, like Apple, for example. And so they have quite successful, because so there is TMSC that is fabricating for them. So TMC, they do not have design, but they do fabrication. So you send the design, they do fabricate with 1 nanometer or 2 nanometer of resolution. And in this way, so TMC is getting care of all the risk associated to the fabrication, but not on the design. And NVIDIA is taking care of all the risk about the design, but not on the fabrication. And without less money, so we are following the very same scheme. So we do the fabrication, we do the design, and then the testing is done.
Which strategy is better?
Sorry?
Which strategy is better?
Which one is better? So this is a philosophy. So are better orange or apples? It's the same. From my point of view, it's better my way. And the reason is because I have not to invest to keep update the technology facility. Because those are a huge investment, okay? And then from my point of view, this is a good way because I have not to specialize on problem associated to the actual fabrication. On the other side, for them, is also a good choice because they do concentrate on keeping update the facility. They do concentrate on keeping know-how how to do the fabrication, but they do not care about the kind of application the circuit that they do fabricate have. Okay, so where is the revenues? Here the revenues came from people that are asking, because the state-of-the-art fabrication is there, so people are asking to fabricate the circuit, and this is their business. Our revenue is coming from the fact that we do, at the end of the day, so we have a system that is working that we can sell. Okay? So in a way, so this is a positive feedback on both. Okay? Anyway, this is how it works. So this is my lab. So this is the people in the lab. And so we have 5 professors in the lab. We have more or less 8-10 postdoc, 8-10 students, and master students as well. And if you are interested, you can go there and you can visit the website of the lab. And so now what we are essentially working on are 3 different topics. I will tell you something about those during my lectures. So we are working on neuromorphic photonics, so a photonic that gets inspiration by the brain. So then we are working on non-Hermitian photonics or topological photonics. So this is very, very theoretical research. And then we are working on, who is this? Is it alive or dead? You don't know the Schrödinger cat, the paradox, the Schrödinger paradox. Okay, so I will try to tell you the Schrödinger paradox. Anyway, so then we are working on quantum photonics as well. And so those are the activity in the lab. So during this giant course, I will touch all those different topics. So today, silicon photonics. Then today, I guess, microresonator. Then optical network on chip. And then neuromorphic photonics. And those are essentially topics that are based on classical electromagnetic theory, okay? So those are classical stuff. Huh? I already showed electromagnetism, Maxwell equation. And then we do also have activity, and during the course here, I will also touch activity on quantum, where essentially the Schrödinger equation take place. And on those, I will first introduce quantum photonics to you. Then I will talk about entanglement, which is one of the most important properties of quantum physics. And then I will show you a couple of applications on of the entanglement, both on single photon sources as well as on quantum security. Okay? So here is more or less my plan. I will also try to follow the schedule, but I'm sure that I will miss the exact sequence that Anamika has written in the notes, okay? So I prefer to go slow and try to get you to understand what I'm saying instead of covering everything. And for this reason, I try to give you the physical intuition about what we are doing. And I will use very, very, very few equations, okay? No mathematics here. A lot of physics, a lot of hand-waving arguments. I want that you understand. In case you do not understand, so you can come to me, and then we can go through all the details. Or you go through all the details, because I'm no longer able to follow. So let me start with silicon photonics. So the past, as I said, I start working on 3.5 semiconductors. So this is a review paper that we published in 1994 on 3.5 semiconductor. And then at that time, so there was a big challenge because people were saying, so if God wanted ordinary silicon to be used as an optoelectronic material, it would have not given us gallium arsenide. So why do you want to work with silicon if gallium arsenide is there? Why you want to work on silicon if indium phosphide is there? So you know what indium phosphide is. You know about semiconductor. You know. So what is the main difference between silicon and indium phosphide? Any answer to this question? So here there is noise. I'm an old guy, so I do not understand correctly. So say loudly. Sorry? Perfecto. Yeah, so this is one of the main difference between the two. In a while, we will see also other difference. So one is a direct band gap semiconductor. The other one is indirect gap semiconductor. But then, in 1990, this guy here, at that time, he was a postdoc or a young PhD, just finished the PhD. So he wrote a paper that is going to be one of the most cited papers in physics. And this paper was saying that, you see here, so you have a piece of silicon wafer, which is glowing in the orange under blue illumination. And so he was able to show it, to demonstrate that if you dissolve partially by using an electrochemical reaction, you dissolve partially silicon, you get very small silicon wires, or very small silicon dots, and those are able to emit light very efficiently. So this material is called porous silicon. And so porous silicon was really a game changer because it was demonstrated that by using silicon, you can get out a lot of light from silicon. And you know that getting out light means that you can get a laser. And if you can get the laser, so then photonics is available. And so let me go through what are the main silicon limitations. So what are the main problems with silicon? So one we already said, so is the indirect band gap. But the indirect band gap means that you have a low radiative recombination probability. So the probability, so the time that an electron hole pairs take to recombine by emitting a photon is very long, millisecond. You know, in 3-5 semiconductor, in gallium arsenide, you have few nanoseconds. And so that means that an electron hole pair in gallium arsenide is moving around, and after 10 nanoseconds, it emits a photon. In silicon, so they do go around, and then after 1 millisecond, they do emit a photon. And so this is the problem. So because silicon is a semiconductor, and therefore the carriers are free to move, and so in silicon, the non-radiative recombination prevail. And that means that if you have 100 nanoseconds for a non-radiative recombination time, and so most of the carriers do prefer to recombine through non-radiative processes instead of recombine through radiative processes. And therefore, so you have a very low quantum efficiency in bulk silicon, 10 to the minus 6. So the quantum efficiency is the ratio between the radiative to the total recombination probability. So if you have a number here that is 10 to the minus 6, it means that every million of electron hole pairs, you get one photon out. So the probability to get a radiative recombination is 1 over 10 to the 6. And so you excite 10 to the 6 electron hole pairs, and you get only one, thank you, and you get only one photon out. So very poor. So can you imagine? So you drive your lamp with 1 ampere, and you get out 1 microwatt, negligible. So what Canham was demonstrating and what we were using at that time, so silicon nanocrystal, is that if you reduce now the dimensionality of the system, you can beat the indirect band gap. By beating the indirect band gap, I mean that you can avoid non-radiative recombination. And so this was the material that at that time so we were producing. So it's called low-dimensional silicon or silicon nanocrystal, very tiny pieces of a crystalline silicon. Look here, 1.5 nanometer, where quantum effects dominates, very tiny nanocrystal. Here is a colloidal suspension of those tiny nanocrystals. So you dissolve those nanocrystals in a liquid, and then you shine blue light, and they glow very efficiently in the red. And so here you have two effects. So the first effect is the fact that the emission, so the typical band gap of this silicon nanocrystal is in the red. And so you have a quantum confinement effect that broadens, that widens the band gap. And the second effect is that you get a very efficient emission. And so those two effects are associated to, first, quantum confinement, so the band gap of the nanocrystal with the dimension of the nanocrystal. So the smaller the nanocrystal are, the larger is the band gap. So that means that instead of having infrared emission, that is the typical emission that you have in silicon, you have red emission, and so higher energy emission. That show you that when you shrink your electron hole pair, so quantum effects start to become dominating, and so you have emission in the red. But then there is another very important aspect, is the fact that you remove non-radiative recombination. And you remove non-radiative recombination because what happens is the fact that you are quantum spatially localize your electron hole pairs into the nanocrystal. So they are no longer able to move around, and so they do not find a non-radiative recombination center. And so all the electron hole pairs that you excite, they only have to recombine through radiative recombination. And so in this way, we get a very strong emission from porous silicon. And so Canham at that time, commenting one of our paper, was saying, so it appears that we can still teach the old dog of semiconductor a few tricks. just need to be restructured on the nanoscale. And so we were looking at whether it is possible to get something useful by those nanocrystals. And so we published a paper in 2000 about the observation of optical gain in silicon nanocrystals. So the fact that you get this quantum confinement not only increase the emission efficiency, but you are also able to get gain. Optical gain, what does it mean? It means that now we have one of the key ingredients in order to make a laser. You know a laser, light. A laser is a device that is used to source coherent light. And in order to make a laser, you need to have an optical cavity, so this is easy. 2 mirrors, easy. But then you need to light beam. At the exit of the material, the light beam is stronger than it was at the entrance. And so the excitement was about the fact that we indeed were able to prove that here you have a transmission spectrum as a function of the wavelength. And what you see here is the transmission, how the transmission increases when you start to pump, when you start to get population inversion into the nanocrystal. And you see that the transmission is getting larger than 1. Larger than 1, it means that you have net amplification. So you enter with the beam and you exit with something that is stronger. And so we were very excited because we were thinking, wow, now we can make an injection laser. And so then we start to get injection. Yes? Yes.
You can make it radiative, right?
Yes.
So now when you reduce the size of silicon, let's assume that you are making a silicon nanowire, how do you get rid of the surface states?
That's a good question. So the question is the following. So if let us assume to have 2 nanocrystals, okay? No, let us assume to have a defect center in silicon, in bulk silicon. You have a defect center. So what density is going to be? 10 to the 14? Okay? So you have one center each 10 to the minus 14 cubic centimeter, roughly. Okay? So then you scale, and you see that this number means that if you have a piece of silicon that is a few nanometer in size, either you have a recombination center inside, or you don't. Okay? Now you excite an electron pairs in both nanocrystal. So this one will be a blind nanocrystal, a dark nanocrystal. This one will be a bright nanocrystal because you have no center there. And so the overall efficiency will be 50%, which is not bad. So as far as the question about the surface states, so you have, who knows why, you know that the first transistor in 1947 was demonstrated in germanium, okay? And the reason why was used germanium, you know. Are you electrical engineer? Are you supposed to know those stuff? Okay, anyway, so the reason why they developed the first transistor 1947 in germanium was because germanium was the material for radar detectors, no? Germanium dyes radar detectors. And so they started working and developing electronics by using germanium. But then they shift to silicon. What is the reason? Why? Why they move from germanium to silicon? Any insight? Yes? What is the reason?
The number is 32 in case of germanium. So the distance is more. So initially when we apply some energy or in what we can say the temperature is rise, so easily electrons can free from the last orbit. In case of germanium.
In case of germanium, yeah. But the reason is another one.
To reduce the surface states in the case of silicon.
Move. Why? That's a good point. Why? So they move from germanium to silicon because of silicon oxide, thermal oxide. Because the fact that if you take a piece of silicon, you expose this piece of silicon to ambient, immediately you have the formation on top of silicon oxide. And what is the use of silicon oxide? You have several uses of silicon oxide. The first one is the fact that you can make a field effect transistor. Okay? You need the gate, you need the channel, and then in between you need the oxide. And this is silicon oxide. It's very easy to make. Very high quality of the surface. And this is the reason why we do not have in the silicon nanocrystal, we don't have the defects, surface defect. Because the quality is almost perfect. Yeah? And then the reason why you need to have silicon oxide and the relevance of silicon oxide, because it is an ideal hard mask. When you are processing your integrated circuit, you need to locally change the properties. And in order to locally change the properties, you need to mask the surface of your wafer. Say that I do want to implant here, but I do not want to implant there. How can we do that? We use silicon oxide. We open a trench into silicon oxide. We let the ions going through. And then where you have silicon oxide, the ions do not go through. And so you have an hard mask. So from a technological point of view, the fact of having silicon oxide is really the reason why they move from germanium to silicon. Anyway, but the problem with silicon oxide is that it's in oxide, so it's an insulator. So it's very tough to inject through the insulator. And this was our limiting factor in order to make a laser. So here you see the fact that we are able to make an LED, so the LED is quite well behaving. So this is the optical power density that we get out of the LED as a function of the current injected. So we were able to inject current by using the tunnel effect, another quantum mechanism. However, here you see the power efficiency. How many watt of optical light you get out of the LED versus the electrical power that you use to drive. And the number is extremely low, 0.1%. Typical LEDs have a number of 50%, 70%. And this is and the problem here is a physical problem. So you have the nanocrystals that are immersed into silicon oxide. You cannot get electrical carriers going through. And therefore, so you have a gain, but you cannot make an injection device. And therefore, so we stop this activity. Even though stopping this activity, so this activity proved the fact that you can turn silicon into a photonic material. And indeed, one of my most cited papers was in 2000, where I was saying that I was questioning the audience about the fact whether silicon will be the photonic material. And indeed, as I will show you, the answer is yes, is the photonic material of the third millennium. So, conclusion. So, when you find yourself competing with silicon, don't. Meaning that silicon will always prevail. But the lesson could also break down saying that silicon, despite being imperfect, despite being an indirect bandgap materials, always win because there are so many opportunities with silicon that people solve the problem. Okay, so let me tell you a little bit about silicon photonics. What should I do? Should I go up to 12? Then we make a break. Okay. So let me talk about silicon photonics. So silicon photonics is a platform where what we do is that we heavily integrate photonic devices by using silicon processing. So the state of the art. So integrated silicon photonics, why we want to, and what are the problems with silicon photonics with respect to silicon microelectronics. So let's go to the heart of the problem. So the real truth of semiconductor industry is that you use large-scale integration in order to make smaller, cheaper, and faster devices. Okay? And everything is dictated by what in 1965 Gordon Moore was essentially suggesting. So the fact that if you put more component into integrated circuit, you get better performing devices. And he was saying, so those are numbers so this is a trend that he proposed, just looking what happens in the early days of microelectronics, and was saying that, so I bet that, you know Gordon Moore, so the founder of Fairchild Semiconductor, of Intel Semiconductor, and so on. And so he was saying that I bet you that the evolution will be an exponential evolution in the next year. And this was said in 1965. And the Moore's law was actually followed, is indeed followed also now. And so the idea is to try to reduce the size of the transistor in order to be able to integrate on the very same surface more and more transistor. And this is what happens in the last year. So you have that the sizes of the transistor are going down. So I was reading yesterday that there are people that are claiming that in a few years they also will produce transistors which are 2 nanometer in size, so 40 silicon atom. And at the same time, so the number of transistors per integrated circuit is increasing, and nowadays we are in excess of 10 billions of transistors per integrated circuit. We are approaching the number of neurons that we have in our brain, okay, in a single transistor. So there are more transistors than okay, I missed the word. Anyway. So this is the evolution of the silicon microelectronics. At the very same time, so we are in the 1960s, also Stuart Miller from Bell Labs was saying that, okay, I'm quite convinced that if we miniaturize the optical circuit, so then we will implement a new technology. Remember, Gordon Moore, 1964, 1965, Stephen Miller is 1969. So the first laser was demonstrated in 1960. The first injection laser, so semiconductor laser, was demonstrated in 1962. So we are really at the early days of the photonics. And at that same time, so he was saying integrated optics. However, if we do compare these two technologies, we see that with photonics, so the number of circuit integrated, the number of photonic component integrated in the very same photonic circuit is very small. So here is an example with indium phosphide photonic integrated circuit, and you see that we only are able to integrate something in between 100 and 1,000, which is a number that is significantly smaller with respect to what they are doing with silicon microelectronics. What is the reason? Why do we have this huge difference? So let us see how semiconductor microelectronics is going. So you have, as a technology, you have a repeatable building block, so the transistor. When we say 10,000, 10 millions, 10 billions of transistor. So we have a single circuit that is dominating. And then we have a uniform material base that is silicon. And then we have a dominant manufacturing process that is CMOS. While if you look at the photonics, before the success of silicon photonics, so you have that many different components you need to integrate. You have that you need many different materials in order to make your system, and you do not have any manufacturing process. Here is an example of a transistor, of a transceiver a few years ago. So this is expert Dr. Singh here. So it is a QPS key, is for coherent, 100 gigas, so a few years ago. And then if you open the box, you see a lot of different components. So here you have a multiplexer, you have a Mach Zehnder, you have some mirrors, you have the laser, where is the tunable laser. Here you have a beam splitter, you have an isolator, you have a driver circuits, and so on. And so what it emerged here is the fact that you need to have a huge amount of different materials in order to make a single device, a single system. And so this is a huge difference between what was happening in photonics with respect to what is happening in semiconductor, in microelectronics. And so here is silicon, so the potential of silicon photonics. So in silicon photonics, what we are trying to do is that we are trying to use a standard platform for photonics, as much as was done with microelectronics. And so in this case, so we are trying to use silicon as a material, and we are trying to use CMOS as a manufacturing process. Okay, no other processes, only CMOS. And then we are trying to reduce the number of building blocks. Clearly, we need to have a laser. Clearly, we need to have a photodetector. But then we are trying to use a micro-ring resonator as a transistor. I will tell you more about that. And the reason why is very simple, because we want to exploit the potential of photonics, meaning the fact that we have many different wavelengths. And so what we can do is that, so here is an example of a transmitter where you can integrate lasers, you can integrate modulators, and then by using different wavelengths, as well as by using increased speed. So what you can get a terabit, so meaning a link that is able to send a terabit per second of information. So then this is the motivation of silicon photonics, and this is what I do mean by silicon photonics. So by silicon photonics, I do mean photonic devices that are produced within standard silicon factory and with standard silicon processing. And the key words here is standard. And this is the reason why we do not have to have our own fab, but we can send our circuitry, our design to any fab, and they are able to produce our circuit, our design. So with silicon photonics, we try to follow the same path as with silicon, so along the year. So we initially demonstrate all the different components, and then we do integrated all components together. So what are the advantages, or what are the disadvantages of silicon? So those are the advantages. So the first one is that silicon is transparent where optical communication happens. So silicon is transparent in the wavelength region between 1.3 O band and 1.5 C band, second and third telecom windows. So that's great. So the second, and this is, anyway. So the second big advantage of silicon is that you can make the silicon photonic circuit by using the same industry that is used to make microelectronic circuitry. NVIDIA has a large program in silicon photonics. IBM, large program in silicon photonics. Intel, large program in silicon photonics. So all the electronic industries have TSMC has a large program in silicon photonics. So all the large microelectronic industries has a program in silicon photonics. So then another advantage is the fact that silicon is cheap. So here is a comparison. A few years ago, I did this comparison, 2009. Oh, time is flying. So the comparison of the typical wafer size, silicon, indium phosphide, gallium arsenide. So 300 millimeter with silicon, only 6 inches with indium phosphide, 8 inches with gallium arsenide. And then the cost of the wafers. So 50 euros for silicon, 500 euros. Large gallium arsenide wafers cost 500 euros. And then, since the size of silicon is so large, you can squeeze 10 billions of transistor in. And therefore, so the cost of the single die is extremely low. And so here you see that there is a huge cost advantages if you move from silicon, from a 3-5 semiconductor to silicon. So then another big advantage of silicon is the fact that you have a very high index contrast between silicon and silicon oxide. So silicon is, yes?
Go back to your previous slide. Can you please go back to your previous slide?
Yes, which one?
Yeah. So, when we are talking about the silicon photonic integrated circuits, so I've seen that whenever I've gone through literature, most of them are fabricated on SOI wafers. Most of them. Now, if you compare the cost between SOI and a typical gallium arsenide wafer, the cost is, the difference is not much.
At the wafer level, yes,
Yeah.
but the size, yes. The
Okay.
size is different, and
Okay.
therefore the cost per die is smaller.
Okay.
But I do agree with you on that. But then there is also another problem with 3.5, and is this problem here. So the high index contrast that we have with SOI wafer than with silicon. And that means that in indium phosphide, in these wafers here or in this die, so we have less integrated, less circuit, less component than in silicon. Because if you see, and this means that the cost for component is larger. And if you see here, so the high index contrast means a small footprint. Indeed, small footprint, why? Because if you take a fiber, an optical fiber, okay, and you start to bend the optical fiber, what happens? If I start to bend an optical fiber, what happens? Okay, so two things. So the first one is that if we bend too much, so we break the fiber. Okay, so we need to avoid. But what is even more for us problematic is the fact that as we bend, so light is escaping. So we have a power loss. And so the bending radius is how small we can do our device before losing light, optical power. And so what is shown here is the fact that the bending radius decrease as you increase the refractive index contrast between the core of the waveguide and the cladding of the waveguide. So the larger is the contrast, the teeny is the device that you can make, because you can do a very small bending radius. And here is an example where you have silicon and silicon nitride. Silicon nitride is another dominant material in silicon photonics, and especially for quantum photonics. I will tell you more about that. But silicon nitride has a low refractive index with respect to silicon. And what you see is the fact that the bending loss in, what should I show here? And so by increasing the refractive index contrast with silicon nitride, you can get a bending radius that is of the order of 500 nanometer, while with silicon you can go down and you can get a bending radius that is of the order of 10 or 15, not nanometer, micron, sorry. And what is relevant here is the fact that now, if you consider the very same component, this is an array waveguide, so it's a multiplexer, demultiplexer component. By simply looking at the refractive index contrast, you get an increase in the density of 1 million. And so this is the kind of contrast that you get with indium phosphide and indium gallium arsenide phosphide, so few percent, okay? And then you need to have 5 millimeter in order to accommodate this device. But then if you go to silicon, you get a very large index contrast between silicon 3.4 and silicon oxide 1.45. Very large index contrast. And therefore, you can squeeze everything on a very small footprint, 50 micron. And so that means that on the very same space, you get an increase in the density of over 1 million. Okay? However, the index contrast has another problem. So in silicon and silicon oxide, we have a large index contrast, but this is also questioning on the fact that this large index contrast means that it's very difficult to couple light into silicon circuitry. Why that? The reason is simple, because the typical size of an optical fiber where the signal is coming and where the signal you want to send, the typical size of an optical fiber has a dimension of roughly 10 micron in diameter. And so this is the kind of channel through which you get your light signal, or into which you want to send your signal. On the other side, since they are high index contrast, single mode silicon waveguides have a dimension of a few hundred nanometer. And so you see that you have a very large size mismatch here. Okay? So you have to get light from this optical fiber and channel into this very tiny silicon waveguide. And so you have this problem. How can we solve this problem? Any insight? You know the answer, right? Okay, grating couplers. So this is one option. Another option?